Hello and welcome back to my channel. In this video, I'll be talking about Leetcode problem number 42, which is called trapping rainwater. First of all, let's see what the problem is. The problem statement is given as such. Given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it is able to trap after raining. As an example, after raining on top of this elevation map on the left, the output would become this map on the right because the water, blue, will be trapped in between each of the black bars and the excess water will fall off to the side. In this video, I'll be covering three methods of computing this sum, which are brute force, dynamic programming, and dynamic programming with space optimization. For each of these three methods, there is some basic logic that I'll be using. First, we have to split the whole map into columns, which are each bar, and find the maximum height of a bar on the left and right side of the current column. After finding those values, the amount of water trapped at that point will be the minimum of the left maximum and the right maximum minus the existing height at the current position. This is the formula we'll be using for the rest of the video for each method. We need to apply this formula for each and every column in the map except for the first and last positions, because it's not possible for the first and last positions to hold any water, since the water at those positions will just flow off to the side. Now let's take a look at the first method, which is brute force. For this method, we first have to iterate through the whole array, and for each iteration, we have to iterate through the values on the left side of the current position to find the maximum of those values, and also iterate through the whole right side of the array to find the maximum of that side. After that, we can use the formula that I mentioned above, which is the maximum of the left max and the right max minus the height of the bar at the current position. The time complexity for this algorithm is O of n squared, because for each iteration that we go through the array, we have to iterate through the whole array once. For those interested, here's how I coded it in Java. As you can see, I store a left max and a right max, initialize them to the first and last values in the map, and go through everything on the left side of I and the right side of I, and apply the formula to find out how much water we can trap at the current position. Now let's go through an example to show how this algorithm works. First of all, we start I from 1, since we know that no water can be trapped at the first position. With I at 1, we have to check the whole left side and right side, the left side being the index 1 and the right side being all of the indices from 10 to 1. After searching, we can find that the left max is 1, which is represented by this bar over here, and the right max is 3, which is represented by this bar over here. Now we can apply the formula minimum of left max and right max minus the current height, which is minimum of 1 and 3 minus 1, which just gives 0. This we can see because the water, if any water rains on top of this bar, it will just flow off to the side. Now we increment I to 2, and we find that the left max is still 1 and the right max is still 3, but now the value at the current position is 0. So therefore, using our formula, minimum of 1 and 3 minus 0 will give us 1, which is the amount of water at the current position of the array. Now we have to keep doing this for the rest of the array. For I equals 3, we find that the left max is 2 and the right max is 3. So using our formula, minimum of 2 and 3 minus 2 will give us 0. And that is the water at the current position. Next, we find that the left max is 2 and the right max is 3. The current height is 1. So the water level at this position will be 1. This is continued for all of the rest of the positions in the array. This was the first method, brute force. The next method that we have is dynamic programming. The intuition for this method is as follows. If we can find the left max and the right max for each and every position before the loop, then we can cut down the runtime from O of n squared to just O of n. To do this, we have to keep two arrays, left maxes and right maxes, which we have to make such that left maxes at I will be the maximum value on the left side of I, and right maxes at I will be the maximum value on the right side of I. To create these two arrays, there are two steps. The first step is to initialize the first index to just be the height at that position, and the maximum value for the other positions in the maxes array will be the maximum of the height at the current position and the max value of the previous position. This is the same for both left maxes and right maxes, except that they are both reversed in order. Once again, this is how I coded it in Java. As you can see, for the left side, this is step 1 and this for loop is step 2, and for the right side, this is step 1 and this for loop is step 2. After creating the two arrays, all we need to do is go through each position and apply the formula I mentioned above to the left maxes and right maxes at I. And again, let's go through an example to show how this algorithm works. First, let's start with the left maxes. In step 1, we have to initialize the first one to the height at 0, which in this case is 0 over here. And we have to follow through with step 2 for the rest of the array. For these two positions, where I equals 1 and 2, the maxes will be 1, and for the next few until it gets to 3, maxes will be 2, and for the rest of the array, the max will be 3. We do the same thing for the right hand side. We first initialize the right side to the height at the last position of the array, and then we fill in the rest of the max values. Now that we have created the arrays left maxes and right maxes, we can find the minimum of the maxes for each position and subtract the height at each position from that minimum value, and then we can get the water level at each position using that. Then we can just sum up the water level at each position and we get our answer. This was the solution that uses dynamic programming. This method has an optimal O of n runtime. However, it still uses two auxiliary arrays in order to work. We can still improve on this with our third and final method that I will show to you today, which is dynamic programming with space optimization. The intuition is that instead of keeping a whole array for the left and right maxes, we can calculate the left and right maxes while calculating the water level at the same time. This is done by keeping two pointers, I and j, I going from the left to the right side, and j starting from the right side and going down to the left side. Using I, we can know the maximum value on the left side of I, and similarly, we can know the maximum value on the right side of j. Using these four values, left max, right max, and I and j, we can come up with four conditions that we need to check for each iteration. The first two are that if the value at I or j is greater than or equal to the left max or right max for the respective side, then we just need to update that side and increment or decrement the counter. Increment for I and decrement for j. If both the value at I is less than left max and the value at j is less than right max, then we have to check if left max is less than or equal to right max. If left max is less than or equal to right max, then we know the water level at I will definitely be bounded by left max, since whatever the case with the right side is, there's at least one bar that is higher than the left max. Therefore, the water level at I will be equal to left max minus the height at I. Similarly, if right max is greater than left max, the water level at J will be equal to right max minus the value at J. This method also has an O of n runtime, since we only do it in one pass, but the extra benefit over the second method is that there is constant memory usage, since we only have left max and right max, and we don't make any auxiliary arrays. Again, this is how I coded it in Java. First, I create a left max and right max, initialize them to the left and right positions of the array, and create two counters, I and j, I starting from the front and j starting from the back. And while I is less than or equal to j, I first check the first two conditions, and if none of those conditions are true, then I check whether left max is less than right max or not, and I calculate the water level accordingly. Once again, let's go through an example on how this is done. We initialize left max to be the leftmost position, which in this case is 0, and right max is the rightmost value, which is 1. I and j start from 1 after and 1 before those positions. For this iteration, the first condition is met, so we just have to update left max to height at I and then increment I. Now the value at I is less than left max. However, the value at j, which is 2, is greater than right max, which is 1. So therefore we have to update right max to be height at j. So we decrement j and update right max. Now both the value at I is less than left max and the value at j is less than right max. So we check whether left max is less than right max. Since it is, we know that the water at I is equal to left max minus the current value at I, which is 0. Therefore, we can just fill in the water over there and increment I. Again, left max has to be updated since the height at I is greater than or equal to left max. So we update that. Now, once again, left max is less than or equal to right max. So we put in the water at this position using the formula left max minus height at I. Left max is 2, height at I is 1. So the water at this position will be 1. Same thing for this position, except height at I is 0. So the water is 2 minus 0, which is 2. And the water level over here is again 1. Now once again we have to update left max, since the value at I, which is 3, is greater than left max, which is 2. Now the first two conditions are not met, so we see that right max is less than left max. That means the water level at j will be bounded by right max. So the water at j will be right max minus the value at j, which is 2 minus 1, which is 1. Now I and j are at the same position, but we still have to carry through with the iteration, since some water could possibly be at this position. However, we see that height at j, which is 2, is greater than or equal to right max, which is also 2. So we update right max and decrement j. Now, since j is less than I, we are done with the algorithm, and we have calculated the total amount of water that is trapped. And this is how the third algorithm works. And that is it for this video. I went over 3 methods of how to implement trapping rainwater, which are brute force, dynamic programming, and dynamic programming with some space optimization. Thank you for watching this video. If you have any questions or comments, please leave it in the comment section down below. And don't forget to like and subscribe to the video. Also, don't forget to check out my website at chatterjeetutoring.com. Thank you for watching. See you in the next one.